Hello there, Mr. Sutton here, bringing you the AB Calculus 512 Extra Practice number 1 solutions on FTC free response practice. For this free response problem, we have a continuous function f defined on this closed interval, and the graph down here is just a portion of f. The interval for f is -6 to 5. This graph, you'll notice, only goes from -2 to 5. So there's some things they're not showing us here. What they did show us, though, is that our graph has 2 line segments, and this is a quarter circle, which is good to know, centered at the point 5, 3, and they also told us that we're going through the point 3, 3 minus radical 5. So for whatever that's worth, that's that point right there. The first part of this problem, they want to know if the integral from -6 to 5 of f of x is 7, what's the value of the integral from -6 to -2? Show the work that leads to your answer. All right, so what they're basically saying is the area under the curve from -6, which we can't see, all the way to 5, that whole stretch of area comes out to 7. What they want to figure out is the value of just -6 to -2, just the part that we can't see here. So we know the area of the entire thing. We could find the area of this piece that we can see using some geometry. So we can use those two areas to find the area of the part that we can't see. In general, we can say that this the area that we're looking for, integral from -6 to -2, is going to be the whole area, integral from -6 to 5, minus this area that we can see, this area from -2 to 5. Because I want to get just a piece of it, so I have to take the whole area and subtract the part that I don't want, which is pretty much everything after -2. All right, so let's see what this comes out to. They already told us that this first integral has a value of 7. And for this next one, we're going to have a big area made up of several shapes. And I'm going to put this in a big parentheses now to calculate it. So I'm going to have minus, and then in a parentheses. So going from left to right, we've got this triangle right here, which has a positive area, at least before we subtract everything. That's 1/2 times a base of 1 times a height of 1. Then we have this triangle down here. This is going to be initially negative before we subtract it. So we're going to say minus 1/2 times a base of, this is 1.5, so 3/2, and then times a height of 1. Next, we have this triangle from 1/2 to 2. So this is going to be 1/2 times a base of, now this would be another 3/2, and a height of 3, and we're adding that because that's initially a positive area. And then finally, we have the area under this quarter circle, which is its own level of trickiness here. So there's no formula for the shape that's represented here. So what we're going to have to do is think about a whole rectangle here, or I guess it's a square. You're going from 2 to 5, and we're going up 3 as well. So we're just going to take this whole square of area and subtract the portion that's a quarter circle, and that'll give us this leftovers that we actually want to find the area of. So the area of the whole rectangle that I'm going to add here is going to be 3 squared, because it's a square. And then for the quarter circle, we're going to subtract this now inside this parentheses. This is going to be minus 1/4 pi r squared, and r in this case is 3, so 1/4 times pi times 3 squared. And again, all of this stuff in here, this is area that we are subtracting from 7. So let's see what this comes out to. Now, you actually don't have to go any further. This is all constants. You could actually stop right here. This is numerically equivalent to the answer. If this is the real AP exam, I would stop right here and call it a day. But since it's not the AP exam, I'm just going to simplify it as much as I possibly can, just for the sake of simplifying it. So distributing this negative and doing the other number crunching in here, we've got a 7 minus, this is a 1/2 here. And I'm just going to simplify things inside the parentheses first. We also have, let's see here, this is going to be minus 3/4. Over here, this is going to be 9/4. So plus 9/4 plus 9. This is going to be, let's see, minus 9 pi over 4. All of that in the parentheses. And if I clean things up a little bit on my next step here, we've got basically 2/4 minus 3/4, which is negative 1/4. Negative 1/4 plus 9/4 is 8/4. 8/4 is really just 2. So we have 2 plus 9 minus 9 pi over 4. And then let's see here. This is really, we're negating this whole parentheses, so we have a positive 9 pi over 4. And essentially doing 7 minus 11, which is going to be negative 4. So we have 9 pi over 4 minus 4, and it's not going to get any better than that. On this part of the problem, they want us to figure out the integral from 3 to 5 of 2f prime of x plus 4 dx. So I'm going to use my properties of integrals to actually split this up, and I'm going to take this 2 out of the first integral. So I can rewrite this as 2 times the integral from 3 to 5 of f prime of x dx, plus, and then I'll have integral from 3 to 5 of 4 dx. All right, well, this is really, this first one, just using my fundamental theorem, antiderivative of f of x is just f of x, or the antiderivative of f prime, I should say, is just f of x. So I can write this as 2 times, and now I'm just evaluating f of x from 3 to 5. So that's going to be f of 5 minus f of 3 in there. Plus, now this stuff out here, this is essentially just a rectangle with a base of 2 and a height of 4. So 2 times 4 there. All right, simplifying a little bit more. F of 5, I can actually look that up on the graph. F of 5 is 0, so I have 2 times 0 minus f of 3. F of 3, what is that? Oh, wait, that's that weird point that they gave us in the stem of the problem. So that's going to have a value of 3 minus radical 5. But since I'm subtracting all of that at once, I'm going to put it in a big parentheses here, just so I don't lose anything and mess up my signs. And then out here, 2 times 4 is 8. So you've got all constants at this point. You could actually leave it like this and move on. But if you want to simplify it, well, let's see here. We've got 0 minus 3, and then we have a plus radical 5. So when all is said and done, we have a 2 times radical 5 that comes out of all this. And this negative 3 times 2 gives us a negative 6. Plus the 8 that's already out there is going to give us a positive 2. So 2 radical 5 plus 2 is your final simplified answer. For this part, the function g is given by g of x equals negative 2 to x integral of f of t dt. So basically, area under this curve starting at negative 2. We want the absolute max value of g on the interval from negative 2 to 5. All right, well, at least they're not asking about the interval from negative 6 to 5. That would be a real pain. So how are we going to figure this out? Well, we're basically going to use the candidates test here. We're going to come up, we have to test the endpoints, negative 2 and 5 for one thing. So that's guaranteed no matter what else we find. We're also going to have to plug any critical values for g into this function here. So let's go ahead and find those critical values. To get those, I need to figure out where g prime equals 0. I would talk about g prime being undefined, but since g prime is based off of this f function, which is continuous, I'm not really worried about the derivative there being undefined. So let's come up with what g prime actually looks like first. G prime, if you take the derivative of this integral here with the variable in the upper limit of integration, you're basically just plugging x in for the dummy variable t. So g prime of x is just f of x. And where does f of x equal 0? Well, we can look that right up on the graph. That happens at x equals negative 1, at x equals 1/2, and all the way over here at x equals 5, but 5 is an endpoint anyway, so we were going to test it anyway. So really, the only new values we get out of here that we have to test are negative 1 and 1/2. Now, between the two of these, technically, since you're looking for an absolute max, you don't really need to test 1/2. 1/2, where f prime, or f rather, where g prime is changing from negative to positive, this is a local min for g. So there's no way a local min is going to end up being an absolute max. That's just silly talk. So you don't have to test 1/2, but it turns out I'm going to test it anyway, just because I'm going to need to know what the area acquired up to 1/2 is. You'll see. So let's start testing from left to right here. So I'm going to start with g of negative 2. That's going to just be the integral from negative 2 to negative 2, f of t dt. And this one's pretty easy because you have the same limits of integration. So because those are the same thing, you have an empty integral with 0 area. Not so bad. Let's keep going. The next critical value happens at -1. So we need g of -1, which is the integral from -2 to -1. Well, that's just the area of this triangle here. So that's going to be 1/2 1 times 1, which comes out to 1/2. Great. And then let's do g of 1/2. Now again, we don't technically need to test this one, but I'm going to anyway, because I'm going to need the value of the function up to this point. So this is going to be the integral from -2 to 1/2. So that's going to include the area we've acquired up until -1, which is this 1/2 right here. I'm just going to rewrite that here. Plus, now we have to also add in this negative area right here. So this is going to be 1/2 times a base of 3/2 times a height of 1. So, and I'm subtracting that because this is below the x-axis. So this is 1/2 minus 3/4, or this is 2/4 minus 3/4, I guess you could say, which is -1/4. Okay, next value. We don't have anything else to worry about actually until we get all the way to 5. So we're going to do g of 5 at this point, integral from -2 to 5. So that's going to include all the area we've acquired up until x equals 1/2, plus this remaining positive area here. So I'm going to start with -1/4, and now I'm just going to add the rest of this area to that. So I have a triangle from 1/2 to 2. That's going to be 1/2 base times height, so 1/2, a base of 3/2 times a height of 3. Plus, now I need to do my little my quarter circle getting subtracted dance that I did all the way back in part A. So remember we had to do 9 squared, or 3 squared rather, 3 times 3, minus 1/4 times pi times 3 squared. This is what we did back in part A to get this area under the quarter circle. And all of this is going to come out to, let's see here, we have -1/4, and this is right here going to be 9/4. I feel like we've done this before. We actually did in part A. Plus 9 minus 9 pi over 4. And if you wanted to simplify that, which is a good idea because you're trying to compare this with the candidate's test to these other values here, this is going to be, let's see here, we have 8 over 4, which is 2, plus 9 is 11. So this is 11 minus 9 pi over 4. So now we have to compare. Well, if we're looking for the absolute max, I think we can definitely eliminate this one right here, this -1/4. It's a negative number. There are positive numbers, or at least non-negative numbers out there. So this definitely can't be it. I think we can also eliminate 0 because g of -1 is 1/2, which is bigger than 0. So really, the question is, what's bigger, 1/2 or 11 minus 9 pi over 4? So here we have to approximate a little bit. 9 pi over 4, well, that's, let's see here, that would be pretty close to, let's round it up. Let's round this up to 12 pi over 4. 12 pi over 4 would really be 3 pi. And 3 pi, that's like 3 times 3.14. So I think that's definitely going to be less than 9.5. So we're basically dealing with something that's going to be, this is going to be bigger than 11 minus 9.5, or bigger than a 1.5. 1.5 definitely is bigger than 1/2. So out of all of these numbers, we have to do some mental gymnastics here, but this is going to be the absolute max, the biggest value right there. For this last part of the problem, they just want the limit as x approaches 1 of all this stuff. So before we assume that we have to use L'Hopital's rule, because this looks like a L'Hopital's rule kind of thing, let's just do a quick mental check here. If I plug 1 into the numerator, that's going to be 10 to the 1, which is 10, and we're subtracting 3 times f prime of 1. Well, f prime of 1 is going to be the slope at 1. Looking at the graph, we appear to have a slope of 2, so this would be basically 10 minus 3 times 2, which is not going to be 0. Since one of these things is not going to be 0, we don't have to use L'Hopital's rule because we're not going to get any indeterminate form out of this. So let's just straight up plug in 1 for x everywhere. So we have 10 to the 1 minus 3 times f prime of 1. We already talked about that a little bit. Down here we have f of 1 minus arctan of 1. And now just doing these out to see what they come out to. In the numerator, we've got 10, and we said we were doing minus 3 times 2 because the slope of f at x equals 1 is 2. We're going up 2 over 1. Down below, we have f of 1. F of 1 is just this y value of 1 up here. And arctan of 1, that's a good one to kind of have memorized. That's going to be pi over 4. So we're subtracting that. Now that you've got all constants and you know that this is not indeterminate, you actually could just stop here and call it a day on this one. But if we simplify, we could make this 10 minus 6, which is 4 in the numerator. And you could leave this if you wanted to maybe simplify a little bit more because there's this fraction down here. You could multiply the numerator and the denominator by 4. That would give you 16 over 4 minus pi, and that would be equivalent. So either of these would be fully simplified. On this calculator-based free response problem, we're given the function f, which is defined only for non-negative numbers. They're telling us f of 0 is 5, and f prime is given by this function, which they also showed you a graph of. So that was kind of nice. I mean, we could have graphed this on our own, but hey, they're giving it to us. Sweet. So for the first part of this problem, they want us to use the graph of f prime to determine whether the graph of f is concave up, concave down, or neither. Okay, so if we want to figure out if f is concave up or down or neither on the interval from 1.7 to 1.9, we basically need to know, is the graph of f increasing or decreasing on that interval? So on the interval from 1.7 to 1.9, let's go ahead and actually graph f prime and see if it's increasing or decreasing. So here I am in my y equals. This is f prime right here that I just entered in as y1. And again, I want to make my window for this 1.7 to 1.9 because I only want to look at that window when I'm seeing if this increases or decreases. So let me do window, and then 1.7 for my x min, 1.9 for the x max. Seems like a very small interval. Let's do zoom 0, zoom fit, and see what this looks like. So this is the graph of f prime, and we see that from 1.7 to 1.9, it is consistently decreasing. This is one of those things where you're allowed to just look at the graph and conclude that it's decreasing. You're allowed to just visually look at something and say, hey, that's going down. So f prime is decreasing on there. We verified it on our graphing calculator. Therefore, that means that f is going to be concave down on this interval. For this part of the problem, they want to know on the interval 0 to 3, at what x value do we have an absolute max? Okay, so absolute max is going to happen at either the endpoints or at critical values of f. Looking at our graph of f prime, critical values are going to be anywhere where f prime is 0 or undefined, and f prime is definitely not undefined anywhere, so it's just coming down to where f prime is 0. We see there are two critical values. One of these is a local max, one's a local min, so we can narrow it down a little bit, but because there's multiple critical values, we can't just use the lonely critical value test here. We actually have to use the candidates test. So we're going to have to test out the endpoints and at least the local max in our original function. And we don't know the original function, but we have a value for the original function. So we can use that, the derivative, and the FTC to get some other values. But first things first, we can say that f prime changes positive to negative, so basically looking for local maxes. We know it's going to be this spot right here, but now I have to actually graph it on my graphing calculator. So again, I've got f prime entered as my y1 here. Now for my window, I'm going to go from 0 to 3 and do zoom fit. And after I get a good picture of this graph, which will probably look pretty similar to what they gave me right here, I'm going to just figure out this positive to negative intersection here. I don't have to consider the negative to positive intersection because a local min is not going to give me an absolute max. But let me do second trace, option 2 for 0. And then let's see, let's move a little closer there, press enter a little bit to the left, enter a little bit to the right of the x-intercept, and then enter one more time, giving me 1.7725 and some change. So I'm actually going to label that as point A, just so I can quickly refer to it. And I'm also going to store that on my calculator because I'm going to go back and test it. So let me quit out of there and press the store button, alpha A, and now whenever I type in alpha A, I can get that number back. So at this point, we've got the only critical value that could possibly be an absolute max, and we've shown why, because f prime changes positive to negative there. We have to test out this value along with the endpoints 0 and 3. So testing each of these out now, let's do f of 0 first because they told us that equals 5. So that was an easy one. Next we have to do, or we could do f of a. Now to find f of a, I'm starting with this value of f of 0, which is 5. And to that, I am going to add an integral from 0 to point A of f prime. So just using my fundamental theorem here. And I'm going to have to go on the calculator and do that. So here I am back on the calculator. I've got 5 plus, I did math 9, integral from 0 to alpha a. And then let me do alpha trace for my y menu. And I'll just press enter to get y1. We'll put a dx there. And then enter. This gives me about 5.679, which is bigger than 5. So right now, the x value a is winning this battle for absolute maximumness. Let's do one more point, though. That would be the endpoint 3. So this is going to be 5 plus the integral from 0 to 3 of f prime of x dx. And back on the calculator, now that we've done it once for one point, it's actually a lot easier to do it for another point. I'm just going to go arrow up here and yank my input from before. And I'm just going to go back to my limit here of integration, and I'm going to change the a to a 3. Press enter. And that comes out to about 5.579. All right, so out of all of these, it's looking like a gives us a slightly higher value. So our max happens at x equals a, which we've already labeled it. It's 1.7725, but you could write it again if you wanted to. For this last part of the problem, they're asking for an equation of the line tangent to the graph of f at x equals 2. I'm eventually going to use point slope, y minus y1 equals m times x minus x1. So I need an x value, I need the y value that goes with it for the f function, and I need f prime, the slope of 2. So I'm going to get all these now. To get f of 2, I'm just going to use my fundamental theorem. I'm going to do f of 0, which is 5, plus the integral from 0 to 2 of f prime of x dx. And I'm going to do that on my calculator here. Now in part B, this is some of the work I did in part B of this problem to do my candidates test and find an absolute max. So I'm just going to yank my input from part B, which I left up there already. And instead of going from 0 to 3 on this integral, since I'm doing it pretty much this exact thing, I'm going to just go from 0 to 2. And that gives me 5.623. I can round it off to 3 decimals here. Next, I need to figure out f prime of 2, and I'll do that on the calculator as well. So the good news is I've already got f prime entered as my y1, so I'm just going to do alpha trace y equals y1, open parentheses, and plug 2 into that, which comes out to about negative 0.459. So there's f prime of 2, there's what it equals approximately. Now putting all this into point slope, I have y minus the y value 5.623 equals m, the m value of negative 0.459 times x, parentheses, x minus the x value they gave us of 2. And there's no need to simplify. There's our tangent line.